In this blackboard session, I want to derive the formulas for marginalization and conditioning for multivariate Gaussians, which also are among the very nice formulas that make multivariate Gaussians so nice to work with. So I derive these two results simultaneously. And then my starting point is again a multivariate Gaussian in x and y. For convenience now, I'm going to say that the expectations of both are 0. This is not really a big deal. I can always just insert expectations instead of x, like x minus its expectation and y minus the expectation because of the way it occurs in the quadratic form. But for now, it makes things easier if I just can keep zeros in expectations. I'm going to call the covariances Pxx, covariance of x, Pxy, Pxy transpose, Pyy. So that's the total covariance matrix of the joint distribution. This is f of x and y. Now I know that I'm going to manipulate quadratic forms. So I'm going to have to invert this whole covariance matrix. So I better find some nice rules for how to invert this kind of matrices. Then I have a formula in the appendix of the book, which looks like this. So A, B, C, D, inverse. And this is then supposed to be the same as something that looks like this. So I have an identity matrix here. But I have 3 matrices that I decompose this into. That's the first of those 3 matrices. And we're going to have another matrix. Which looks like this. So here you have this thing called a Schur complement appearing. Then you have some 0 matrices here too, and B inverse. So that's the middle matrix, and then you're going to have another one which is sort of similar to this one. Given some suitable symmetry, which I typically have, or this will be the transpose of that one. The result is more general than that. So, this is my general rule. What does this become in this particular case? Pyx, I could just still have written Pxy transpose. It's the same. So I have my identities. I have instead of D, I have Pyy inverse, Pxy transpose, 0 identity. Then I have this Schur complement thing, which becomes Pxx instead of A, minus Pxy, Pyy inverse, Pxy transpose, and the whole thing inverse. 0 matrix there, Pyy inverse. And then it was the third matrix, identity, 0, minus Pxy, Pyy inverse, and identity. And then I'm going to insert this in here and see what does then the expression for the joint become. F of x and y. So this is going to be proportional to an exponential in -1, of course, 1 minus 1/2. And then I'm going to multiply, basically I just multiply this with this, and in the first part I'm going to take the transpose of that. thing times the y. Then I have this thing times the y. Then I have my little matrix, nothing much happens to that one yet. And then the same thing as I had here, except now I don't transpose it. Y here, and a Y. Okay. Doesn't seem like I have gained so much yet, but now what I can exploit now is that this middle matrix is block diagonal. And this means that I can decompose this into individual, into two products, two factors in a product. The first factor is an exponential that involves this upper left block. It looks like this. Y, dy by inverse y transpose x minus xy dy by inverse xy transpose up to reverse. Same thing again. And then I have the second factor in the product, which comes from this thing. And that's basically all the mathematics I'm going to do. Because in this I have inherent both the marginalization and the conditioning result. If now we look at marginalization, what is that? And that is f of y. This is the same as the integral of the joint distribution f of x and y over x. Now x only occurs in this this thing, this upper exponential, and we can immediately see that that this is a Gaussian in x. So when we do this integration, the first part disappears, and we are left with something that is proportional to this. Of course, there could be normalization constant involved that we haven't looked at, but they don't matter, because I know that this is proportional to a Gaussian anyway, so it is going to evaporate when I integrate over x, and I'm going to be left with this, the second factor, which is then proportional to a Gaussian, and since this is a probability distribution, it has to be a Gaussian. Looking like this, expectation 0, covariance matrix EYY. So that was the marginal. So then I have obtained this marginalization formula, which is perfectly intuitive. When I do marginalization, I should end up with the same expectation as I had and the same covariance. EYY. Look at conditioning then. So then I'm going to get f of x given y. Could of course be y given x2, but the way I've set this up now, it makes more sense to look at x given y. This is the same as the joint, x and y, divided by the marginal. Okay, so I have the full expression for the joint up here. This is proportional to the marginal, which means I'm left with what is up there, the first line. So this is a Gaussian in x with expectation exy, eyy, and this one. And then this covariance terms pxx minus pxy, pyy minus 1, pxy transpose. Now, as I said, if you have some non-zero expectations, well, you could, for example, here, if you have a non-zero expectation for x, you could just say, okay, I'm going to have over there, I'm going to have x minus a, so I have x minus a r2, and then you could take the a over here, so we get a plus this thing. So that's straightforward. Now, when you look at this, you might also recognize that this is entirely identical to what we did for the linear minimum mean square error estimator. So as I said then, we have a reduction in uncertainty because we are conditioning on some information, which should make sense. We have more information, uncertainty goes down. Y appears in this expectation. You have some idea about what Y is, and since there is some cross correlation encapsulated by this matrix, that will shift your expectation of where x is going to be. So then we have both marginalization and conditioning for multivariate Gaussians.